Hello, welcome back. We're going to go over the Chapter 10 practice project. Okay, so for this question, we have a continuous compound kind of question. We have a rate here, and then what do we want to know? If we have this amount invested initially, then what will it be worth in 10 years? So recall that our continuous compound formula looks like something like this. A equals P-E-R-T. All right. And so P is the amount that you put in initially, the amount that you invest initially. And R is your rate at which it is compounded continuously. So we can use that from the number given in the prompt, but R is in terms of a decimal, not a percentage, so we need to convert it into a decimal. So 2.5% is 0.025, and then T. And so for question 1, we want to find A of 10, right? We want to plug in 10 for T, and we want to know when my principal, my 11,997, when that's invested initially, how much is it worth after 10 years? So you just need to plug that into the calculator and you should get 15,404.45. And that's in dollars. So that's our answer for number 1. Right, for number 2, we have a different kind of question. So we know that if we initially invest 10,000, how long will the account be worth 11,582? So now we're looking for T, how long, and we are given the amount that we invest, which is our P, and the amount that it's worth after time T, which is our A. So we're solving for T in this case. So we can form the relationship 11,582 is equal to our P, which is 10,000. E is our exponential factor of growth, and our rate is the same from the prompt, and then we're solving for T. So if we try to isolate T, we can divide out that 10,000 first. Okay, and so I want to isolate T, so what I can do is I can natural log both sides. And so on the left-hand side, I have natural log of 1.1582, and on the right-hand side, I have 0.025T. And so the last step to isolate T further, we can take the natural log of 1.1582 and divide that by 0.025. And we want to round to the nearest tenth of a year, so this will give me 5.9. So 5.9 years. All right. For this question, we have resale value, which is R of T dollars after T years. So we want the rate of depreciation in dollars per year. So that sounds like a derivative, right? A rate. And we want to know after 2 years. So we are most likely wanting to find R prime of T, which in this case is 2. So first we need R prime. Okay, so 17,968, that's a constant, so I can just pull that out. It's being multiplied by something of T. And then I want the derivative with respect to T of 0.772 to the Tth power. All right, so this is not the power rule, because with the power rule, that's when we have x as a base and some constant. But now we have a constant raised to a variable. So that's where we need to use our special rule that we learned in this chapter, where the derivative of b to the x, say, so it's some constant raised to some variable x. This derivative is b to the x times natural log of b. So let's use that form. So my b is 0.772 to the x, so that's my variable t, times my natural log of my base b, which in this case is 0.772. So that's my r prime. And so to find r prime of 2, I'm just going to plug in 2 for t wherever I see a t. And it happens here. And then you can use the calculator to find this. We are rounding to the nearest cent. And so this should give you negative 2771.08. So they also told you that your answer should be positive, and that's because we're finding the rate of depreciation. So this means depreciation just means it's like decreasing. So it already has the negative connotation in it. So that's why you just take the positive value, because we have a negative here. So depreciation means that it's decreasing by a factor of this amount, not negative. All right, so your answer here should be $2,771.08 per year. All right, so let's revisit our continuous compound interest. So here we have an investment of $10,000. So that's our initial principal. It earns a rate, or interest at a rate of this. This is our R, and it's compounded continuously. So we will use the form A equals PERT. All right, so let's look at the questions. It looks like we're dealing with instantaneous rate of change. So that should automatically give you a hint that we need to take the derivative of A. So let's first form A. A is equal to 10,000. That's my principal. E, my rate as a form of decimal is 0.067 t. So that's my amount equation. And so we want the instantaneous rate of change for the amount in the account after 4 years. So we want A prime of 4. Okay, so let's first take the derivative. A prime equals, so 10,000 is a constant, so I can just keep that on the side. And then the derivative of e to anything is e, so you just rewrite it basically, but then you have to chain rule it and take the derivative of the power on e. All right, so if we simplify a little, 0.067t times, and so the derivative of 0.067t is just 0.067. So this is being multiplied by this. And so we can further simplify if you want to be 670e raised to the 0.067t. So now if we want to find A prime of 4, we just plug in 4 for t. And this should give you 875.92, rounded to the nearest cent. All right, and the second question is kind of like the second question, or the second part, I guess, of the first slide. So we are given a amount of this, and we want to know the time, and then that time is what we're going to plug into our derivative. So it has a few steps in it. So maybe I'll use capital T for this specific time that we're trying to find. So to find that time, we want to find when my amount is 14,757. So I'm going to use my amount function first, not the derivative. And I want to solve for t, which we already saw how to do this for our second question. All right, so we get here, we can natural log both sides to bring that power down. And get this. And so t is equal to natural log of 1.4757 over 0.067. And this should give you 5.0879 maybe. I'd bring it out a few decimal places just to avoid rounding error. And so we're not done. That's my specific time. I guess I made it capital T just so it's different. So now we want to find a prime of that t that we just found, 5.8079. So we can plug that into our derivative, which is here. So 670 e to the 0.067 times this 5.8079, and this gives me 988.72. So the answer for this question is 988.72 per year. All right. So now we have a sales analysis question. We have a total sales in thousands of video games given by this equation. We want to find S of 10 and S prime of 10, and we'll use it to estimate the total sales after 11 months. So basically this is saying that we want to find how much sales we've done in 10 months. So that's our starting point, plus the change, the instantaneous change at this point in order to get us to the next month. So like 10 is here, month 10 is here, and month 11 is here. So we want to add the amount here to our instantaneous rate of change, and that should give you the estimated sales for month 11. But anyway, so we need both parts. Well, let's first plug in the constants. So we have 88t squared over t squared plus 48. So if we want to find S of 10, we just plug in 10 wherever I see a t. And this, I believe, I got to be 59.4595. Again, I'm going to bring it out a few decimal places just to avoid rounding error. All right, and then we also will need the first derivative because we want to find S prime of 10. So we can use the quotient rule. I like to try to avoid the quotient rule, so I'm going to rewrite our original function as a product. So t plus 48. But if you feel comfortable with the quotient rule, by all means, go ahead and just take the derivative that way too. So I want to take the derivative of this product now. So that's going to be the derivative of 88t squared. So that's going to be 88 times 2t. And then you rewrite the t squared plus 48 to the negative 1 power. And then you add the 88t squared times, and I'm going to put it right here, the derivative of the t squared plus 48 to the negative 1 power. So this will involve a chain rule. Let's bring that power down first because that's my outer function. Rewrite my inner function of t squared plus 48, and then finish off the power rule, minus 2 because we're going to subtract 1 from the power. All right, and then chain rule it. I need to take the derivative of t squared plus 48, which is just 2t. All right, so I'm going to do a little simplification, but again, you don't have to. This will be 176t over t squared plus 48 plus, what does that become? So 176t cubed, right? These two, if I multiply those two first, oops. And then I can throw this term in the denominator and make that power positive. And then I have this -1 here, so this actually becomes minus. All right, so that's a more simplified version, but you don't have to necessarily do that. Let's throw in 10 because we want the derivative at 10. So 176 times 10 over 10 squared plus 48 minus 176 times 10 cubed over 10 squared plus 48, the whole thing squared. Okay, and a calculator will be helpful here, so let's find it. I got 3.8568. All right, and so our last step is just combining the two that we just got. So 59.4595 plus 3.8568. And I believe this is 63.32 if we round to 2 decimal places. All right. Okay, so for this one we have drug sensitivity. So we have a dose in X milligrams. We have a change in body temperature modeled by T of X. And we also know that the rate T prime is called the sensitivity. So we want the sensitivity to a dose of 2 milligrams. So essentially we want to find T prime of 2. All right, so I'm going to do some simplification because we know we're going to take the derivative of T. I see that there's a product here, but it's always good to do some algebra beforehand that can potentially simplify things and maybe not make you need to take a product rule or a quotient rule. So I would always be on the lookout for simplifying if possible. So if we simplify this, I can distribute this x squared in, get x squared minus x cubed over 8. All right, and that's probably as simple as we can get it. So now let's take the derivative. So notice I don't have to take the product rule anymore. So this derivative is 2x minus 3x squared over 8. And then we want T prime of 2, which is just plugging in 2 for x. So get all of that, and this comes to 2.5. All right, we have a price and supply. So we have a price P, we have some constants given to us, and then we want the instantaneous rate of change of supply, which is our x, with respect to price, when the price is 78. So we want x prime of 78. All right, so let's first form our x with our constants that we were given. P plus 28, and then minus c outside of the square root. I'm gonna rewrite the square root as a power of 1/2. It's just easier to know which derivative rule I will need. So if we take x prime with respect to p, that 78 will just hang out there for a sec. Let's take the derivative of p plus 28 to the 1/2 power. So bring the power down, p plus 28, decrease the power by 1, and then no chain rule here because p is just p. All right, and then the derivative of 394 is just 0. So let's find x prime of 78. That will just be plugging in 78 wherever I see a p. That's 1/2. All right. You can also think of this, if it helps you to see it this way, if we move that 78 plus 28 to the denominator and make the power positive, or we can also return it back to a square root so that you understand that there's still a square root in the answer. And so this comes to 3.79 once rounded to 2 decimal places. All right, blood pressure and age. So we have a blood pressure model here. X is age in years. We have these constants, and we want to know the rate of change of pressure with respect to time after 31 years. So this, again, is kind of sounding a little familiar. We want P prime of 31. So P, let's plug in our constants, 36 plus 29 natural log of X plus 1. So our P prime, that's going to be the derivative of 36, which is just 0, plus, I'm going to pull that 29 out, and then I just need the derivative of natural log X plus 1. And this happens to be 1 over X plus 1. So our derivative is 29 over X plus 1. And P prime of 31 is 29 over 31 plus 1. And this comes to be 0.91 once we round to 2 decimal places. Okay, so here we have a rate of change of cost. We know that we can produce 1 hamburger for $2.45. If our daily sales are increasing at a rate of 30 hamburgers per day, how fast is daily cost increasing? So my cost function, this is equal to my price times how many hamburgers I sold. So here I'm going to call it some function S of X, all right, and where S of X is hamburgers sold. All right, and we also know that my daily sales are increasing at a rate of 30 hamburgers, so my S prime of X, whatever function that is, that's gonna be 30. And so we want the derivative, right? We want the rate of change for the cost. So C prime, that's equal to my price. So that's just going to be a constant here, 2.5. That's what my P is. So that will just hang out to the side times my derivative of S of X, right? We don't know what that looks like, but that's okay, because we know that that rate of change is 30. So now we just substitute that in, and our answer is $73.5 per day. And they say round to the nearest cent, so you can just throw on another 0 if you want. All right. So now let's do our last 3 questions for the project. We have a price-demand equation where demand is our X, P is our price. We want to know what price will maximize the revenue. All right, so first things first, our revenue is equal to X times my price. So we need to solve for P here. So if I do X plus 388, P is equal to 3011. So I can quickly solve for P by just isolating it, and I get P is equal to 3011 minus X all over 388. And so my revenue is going to be X times this amount that I just found, 388. And so let's multiply that through a little. So I get, if I distribute that X through, I get 3011X minus X squared over 388. I can also rewrite this and separate that fraction because there's subtraction here. So 3011X over 388 minus X squared over 388. So that is my revenue function. So notice how I have an X squared here, and that tells us that it's going to be a parabola. The minus tells me that it opens down. So we have some parabola like this where I know that I'm going to have a max at its vertex. And so the max occurs at x equals negative b over 2a, where b is my coefficient of just x and a is my coefficient on x squared. Sorry, a is my coefficient on x squared. So you can kind of think of x squared being here and a is looking like that, and then you can kind of separate them if it helps looking at it like that. So our b is 3011 over 388, and our a is minus, because we'll take the sign with it, 1 over 388. So my maximum occurs at negative 3011 over 388 all over 2 times negative 1 over 388. So we can kind of simplify a little. 388 over, so these negatives, when they are multiplied or divided, they will make a positive. So we can kind of drop this negative sign. And then if we multiply the 2 through the denominator, we get this. And then recall, when we have one fraction divided by another fraction, we can change that to multiplication and flip the second fraction that's doing the dividing. And so I get 1505.5. This is our x that creates the maximum. But notice that this question is asking for the price that maximizes it. So we want to solve the corresponding p to this x. So I'm just going to use our price function here and just plug in that x that we just found. So I get this is equal to 3011 minus 1505.5 all over 388, and this gives me 3.88. So that is the answer here. All right, for the second question, so if the price, or if the current price is this, how will a 2% increase in the price affect the revenue? And 13 is also similar. We have a different price and a different amount of increase in price. So this has to do with the elasticity of demand. I believe this was section 10.7. So we need to find our elasticity of demand function, E of P, and this is equal to negative P F prime of P over F of P, where my F of P is equal to my X. And we found that, well, we didn't find that. I guess we'll have to find that real quick. So starting from our original price demand, if I want X by itself, I just need to divide out that 388p and move it to the other side, or not divide, subtract out. So if I subtract it from both sides, I get 3011 minus 388p. So that is my X in terms of p. All right, so we will need negative p, we'll need f prime, so we'll do that in a second. And then we put this over f of p, which we just found to be 3011 minus 388p. Let's find the derivative of p with respect to p, oops. And so the derivative of 3000 is just 0, and the derivative of negative 388p is minus 388. So our derivative is negative 388. All right, and this can be simplified as those negatives will become a positive when multiplied. So I get 388p over 3011 minus 388p. All right, so the idea is that this is our elasticity function of demand, and when we plug in these price, we can decide whether our demand is elastic, inelastic, or neither. Unit elasticity. And then that will tell us how revenue is affected by an increase in price. So let's first find our elasticity of demand for the price 3.33. So we just plug in 3.33 into this function that we just found. So it will look something like this. And then you'll want to calculate it to see what number you get. I got 0.75, and so you want to look at whether this is equal to 1, greater than 1, or less than 1. So this is less than 1, so this means that demand is inelastic. So an increase in price will increase revenue. So I guess our answer is 1, increase. So now we can do the same thing for question 13. We want to find E of 4.50. All right, so let's plug that into our elasticity of demand, 4.5. 388, 4.50. And if we calculate this, I got 0.38, and notice that this is bigger than 1, so this means that my demand is elastic. So this means that an increase in price will actually decrease my revenue. So this answer is 2. Alrighty, so we just finished up the chapter 10 practice project. Hope you guys are feeling better about this, and keep watching for the chapter 11 project.